Hello, everybody. It's great to be with you, at least virtually. I feel humbled by the very insightful introductory remarks that almost make my contribution obsolete, but I will still try and take you through a few slides that I put together, and just want to thank both TERI and the Carnegie Climate Governance Initiative to invite me and to contribute to this side event. I'll just try and share my slides. And I'd also like to acknowledge a number of inputs that I received from various IPCC authors, bureau members, and technical support units. I would like to stress that any mistakes or judgments in the slides in my presentation are entirely mine. So I'll try very quickly cover what is CDR and what is it good for, what is overshoot and how is CDR relevant to this, what is SRM, solar radiation modification, and how could it complement mitigation, and lead out with some concluding thoughts on challenges, opportunities around governance issues. So a key conclusion from the IPCC Sixth Assessment Report is that limiting human-induced global warming to a specific level requires limiting cumulative CO2 emissions, reaching at least net zero CO2 emissions, along with strong reductions in other greenhouse gas emissions. And that is, of course, simply a result of physical science. There's no political distribution or commitment in that. This is simply what the science tells us must happen. As you're probably all well aware, global warming, which is shown on the vertical axis here, is strongly linearly correlated with cumulative CO2 emissions since the Industrial Revolution. And so it's simply a case of the more CO2 we emit, the more we warm the world. And it is a necessary consequence that net zero CO2 emissions are necessary to halt global warming. We simply have to stop putting carbon dioxide into the atmosphere. Out of that flows, of course, the reverse, that if we want to reverse global warming, we have to actively reverse global CO2 emissions. Because of the long lifetime in the atmosphere, they don't disappear by themselves. We have to actively take them out of the atmosphere. Which leads us to the role of CDR. And a key conclusion from Working Group 3 is that the deployment of CDR, of carbon dioxide removal, to counterbalance hard to abate residual emissions is unavoidable if net zero CO2 or greenhouse gas emissions are to be achieved. And let me just illustrate the unavoidability of that. What you see is a stylized pathway of global CO2 or greenhouse gas emissions in orange. And of course, that is always composed of a combination of gross CO2 emissions and counterbalanced to some extent of total carbon dioxide removal. So at the point of net zero CO2 emissions, it is inevitable that there has to be some amount of CDR applied if we want to get to net zero. And that applies both at country level and at global level, simply because we have no feasible pathway at this point to completely avoid all gross CO2 emissions. So even just reaching net zero CO2 makes the deployment of CDR unavoidable. The only question is, how large is the scale of CDR? And that's driven by how far can we reduce our gross CO2 emissions. But there are very, very few pathways that outline a way to reaching zero gross CO2 emissions. And that makes CDR a necessity, even just to reach net zero CO2 emissions and to halt the continued global warming. Of course, then looking further into the future, we might want to achieve net negative CO2 emissions in order to achieve, for example, net zero greenhouse gas emissions and to achieve declining global temperature, which by and large will imply increased amounts of CDR because of the ongoing assumed residual gross CO2 emissions that need to be counterbalanced by a greater amount of CDR. Now, the IPCC has undertaken a very detailed, comprehensive assessment of a wide range of CDR options. I'm not going to go through them in detail. I would just like to point you to Working Group 3, Chapter 12 provides an overview, but equally Working Group 1 from a physical science perspective in Chapter 5. So it's a comprehensive assessment of the potentials of sustainability, of constraints, of risks and co-benefits, and especially at large scales as well. There's also discussion about the methodologies for monitoring, reporting, and verification of carbon flows. maybe 2 points that may be relevant for our discussion today is that currently afforestation and reforestation are the only mature methods that are widely practiced. But there's a wide range of methods that are either proven in their component parts or demonstrated at very small scales. And as was already mentioned, the key challenge will lie in how can we upscale that. Another tension arises from the fact that biological carbon storage is of course always vulnerable to reversal, either by climate change or by practice changes. But biological carbon storage also has the largest potential for co-benefits if managed well. So these are important trade-offs and risks that need to be addressed by governance issues that we may want to discuss further. Now, on Overshoot, and as already pointed out, it feels like defeat. It is a conversation that we must have in order to navigate our way forward. In the IPCC definition employed in the AR6 report, overshoot pathways are pathways that first exceed a specified concentration, radiative forcing or global warming level, and then return to or below that level again before the end of a specified period of time, often before the year 2100. And this has been used in close alignment with that in the Working Group 2 assessment that looked at the risks of overshoot, but also in the global emission scenarios assessed by IPCC Working Group 3, in particular, 2 scenarios that limit warming to 1.5 degrees by the year 2100, but category 1 achieves that with no or limited overshoot, generally by about up to 0.1 degrees Celsius overshoot for several decades, whereas category 2 implies higher overshoot of between 0.1 and 0.3 degrees Celsius typically. So just very quickly looking at what does it mean to overshoot and what does it mean for emissions. Here's a number of illustrative pathways that don't all limit warming to 1.5 degrees in the long run, that just illustrate different amounts of overshoot, different durations of overshoot and different levels of overshoot. So the blue pathway is what's commonly called a 1.5 degree pathway with no or limited overshoot. The orange pathway does not limit global warming to 1.5 degrees until well into the 22nd century and has a very high overshoot. And then the green pathway is a more thought experiment pathway with a very, very high overshoot during the 21st century that would still reduce global warming to close to 1.5 degrees during the 22nd century. These are just illustrative pathways based out of physical model studies. I'm not saying that they're relevant for policymaking at this point. They're important to clarify concepts used in conversations around overshoot. Now, the important point to look at in terms of overshoots that can be described in terms of the magnitude of overshoot as well as the duration. And the key drivers of overshoot, keeping in mind that overshoot is both the exceedance and then decline of temperatures. The critical requirements, as I said before, are net zero CO2 emissions, at which point the warming stops by and large, and then achieving net negative CO2 emissions. And of course, the lower the overshoot, the more rapid near-term emission reductions are needed. Vice versa, high overshoot relies on large-scale net negative CO2 emissions in the long term. I just want to add that the rate of non-CO2 emissions, especially of short-lived climate forces, is also relevant for overshoot for 2 reasons. One is the rate of non-CO2 emissions adds to the warming from CO2 at peak level, but also a continued decline in short-lived climate force emissions could support a further decline in global temperature. So it's predominantly driven by CO2, but non-CO2 emissions are relevant. And of course, depending on country profile, may be particularly relevant for that country's contribution, but also mitigation options. Now, very briefly, I want to talk about risk, but only very briefly. You'll be well familiar with the burning embers diagrams, which are used by the IPCC to communicate key high-level risks associated with different levels of global warming. And at the global level, there's sort of 5 key embers that cover unique and threatened systems, extreme weather events, the distribution of impacts, global aggregate impacts, and large-scale singular events. It's important to understand that those embers and the literature on which they are based predominantly have assessed how risks increase with warming. What we're trying to confront in the context of an overshoot conversation is to what extent does the same relationship apply in a cooling world? To what extent does cooling then reduce those risks? And just very briefly, for one thing, we have to recognize that risks are a combination of climate hazards, exposure, and vulnerability. And it's the confluence of those three that determine the extent to which those risks are indeed reversible if we manage to reverse the global temperature trend. As far as unique and threatened systems are concerned, for example, once species are extinct, once ecosystems have been rendered incapable of continued functioning, reducing temperature is very unlikely to bring them back. That's a simple fact. As far as extreme weather events are concerned, of course, for example, the frequency of heat waves would expect to drop down again, but that neither brings back the people who were affected by heat waves and by extreme flooding events during the period of overshoot, but also those events in the past may have changed the vulnerability and the adaptive capacity of communities, which means that the risks in a climate where temperature is reduced again may not be the same as the risks were before the climate started to exceed a given threshold. And then in other areas, for example, global aggregate impacts, sea level rise is one of the key risks that drives coastal hazards and impacts, where, of course, reducing overshoot will still have continued sea level rise because we would have to reduce temperature far below the levels that are envisaged, even in the Paris Agreement, if we want to stop sea level rise from occurring. I'll leave it there for the risks. Very briefly, moving on to solar radiation modification. This is often proposed as what's called peak shaving. So if we have a set of pathways, the red line would be climate impacts or temperature as a proxy under business as usual. If we cut emissions aggressively, we might halt the rise in temperature. If we add large-scale CO2 removal, we might be able to reverse temperature again. And then the question arises, could what's also called solar geoengineering help shave off the risks associated with this temporary peak in temperature? That's where I think the relevant conversation about solar radiation modification lies, because if we do not actually have a peak and decline pathway based on emissions, we are committing ourselves to solar radiation modification in perpetuity in ways that would magnify risks associated with it. There's been a fair bit of attention given in the IPCC assessment, both in working groups 1 and 2, and also from the governance side by working group 3, on various ways of solar radiation modification. And I guess the key messages out of that, rapidly condensed by me into a single slide here, is that there is a wide range of possible or proposed interventions. They have different mechanisms, they have different scale, and as a consequence, they would have very different impacts on global, regional, and seasonal climate, both in terms of temperature and non-temperature aspects such as rainfall, depending on their deployment. And that is a very important point. For example, stratospheric aerosol interventions could be deployed such that they mimic the temperature effect of reducing CO2 emissions, but that would require aerosol injections at multiple places in sort of a staggered way around the globe, whereas a single aerosol injection would not achieve a mirroring of the effects on temperature or other climate variables of carbon dioxide removal, for example. But then, of course, those different effects also have different impacts on non-climate aspects such as land and ocean, ecosystem productivity, crop yields, sea salt deposition, biodiversity, and of course, none of those would stop ocean acidification. A concern in that goes back to the deployment of solar radiation modification as peak shaving is termination effects. If we were to stop solar radiation modification after having deployed it, we would expect a rapid increase in global and regional temperatures and associated impacts. So that's the reason why peak shaving is most likely to be manageable in terms of its risks, because there would be a softer landing on the assumption that the global response to climate change in terms of emission reductions would allow such a soft landing and such a gradual exit strategy from solar radiation modification. But overall, we do have low confidence in our understanding. And I need to emphasize, this is all based on stylized model scenarios of deployment. Very few of those have actively considered likely geopolitical drivers that might lead to non-coordinated deployment of solar radiation modification. And just to illustrate, in two maps on the right-hand side shows maps of how much different interventions that have the same effect on global average temperature might affect precipitation patterns from stratospheric sulfate aerosols and marine cloud brightening, where you can see that the impact on rainfall in different regions of the world would be quite different, even though the effect on global average temperature would be the same. So that just illustrates the regional diversity of different solar radiation modification approaches. Very brief concluding slide. I'd really want to leave you with the message that CDR is essential for even just reaching net zero targets for holding temperature. And for that, it's critical that we upscale and develop MRV methods, robust policy mechanisms to deal with impermanence and reversal, especially on the side of biological carbon storage, integration of CDR into mitigation portfolios rather than treating them as a poor cousin. I think CDR is really an essential component of mitigation, and we cannot achieve our stated goals without working towards CDR. Of course, there are risks from large-scale deployment, but I would put to the distinguished audience that these risks are not unique to CDR. There are risks from large-scale mitigation of any nature. There are risks from large-scale deployment of hydrogen as an energy carrier. So areas where CDR presents unique risks are particularly in the area of transfer of biomass, where one country might be supplying biomass for the carbon capture and storage as part of bioenergy, for example, in another country, and the consequences that might have on the sustainability, on food security in that country, which then requires particular governance mechanisms. But by and large, I think risk from CDR are at national and subnational scales, depending on their deployment. CDR is equally essential for achieving overshoot, i.e. for achieving a sustained decline in global temperature after a peak to reach net negative emissions, where the scale required of CDR depends crucially on both the remaining gross emissions that we need to overcompensate and the intended rate of decline. So there's a number of moving parts here. They're not givens out of just saying net negative emissions. But of course, there would be an added dimension to global burden sharing once we reach a state of net negative emissions, but also domestic policy design, because you run out of polluters to pay for carbon dioxide removal. So that requires a different framing, a different role of governments to achieve net negative emissions. On CDR, on SRM, I think it's pretty clear and widely agreed that SRM can complement but not substitute for mitigation. It's particularly effective in the context of a limited overshoot. But limited overshoot in itself relies on a functioning global cooperation to achieve net negative global greenhouse CO2 emissions in order to achieve the peak and decline in temperature in the absence of solar radiation modification, which allows a gradual exit strategy. There's clearly high risks from unilateral deployment, given transboundary impacts and non-uniform responses to SRM, whereas managed and manageable risks, again, rely on functioning global and regional cooperation to design interventions properly. And just as a last thought, when we talk about risks and benefits of both CDR and SRM, it's very important that we are clear about the counterfactual situation. It's clear that both CDR and SRM pose high risks, but the question is always high risk compared to what? Is it high risk compared to a world that addresses mitigation smoothly and efficiently in a way that sadly does not correspond to our current reality? Or is it high risk compared to not deploying those options? And so I think both perspectives are valid and they have different roles in conversations, but it will help us to be always clear risks compared to what in our conversations and in developing governance mechanisms to address them. I've talked for long enough. Thanks very much, and I look forward to the discussion. Thank you.